Right, so Young's modulus. You might start out by thinking, that's a funny word, modulus. But actually, it suits our purposes down to the ground, because a modulus is a constant factor or ratio, which is awesome for what we want it for. Now, before we had these two videos where you were talking about how materials behave under Hooke's law. And what we want to do with Young's modulus is quantify that and give a definite idea of the forces and the extensions that these materials are put under. So how do we do that? Well, let's draw a diagram. Let's say you've got a wire, and in cross section it's going to look like this, and that's only a tiny smidge of it. And this little bit here is going to be given by A, and that's the cross-sectional area. And that wire is going to undergo a force F. And it's much like we had a string or a wire under force from a mass, and that could be mg, something like that. Now the stress is given by sigma, that's the variable we use, and that's going to be denoted by force over that cross-sectional area. The units we use are going to be newtons over meters squared. And you should look at that and think, that looks familiar. That's just a Pascal. So stress is given in terms of pressure. Okay, so the strain is the other variable we have to concern ourselves with, and the way that's calculated or thought about is by considering this wire and considering it extending down here. So you've now got a delta x, just like we did in Hooke's law. Just call it x. So the strain now is written as your extension over your original length. So your original length was here, and now it's extended by this x, and you write it here. Now you'll notice you've got a distance and a distance, so there are no units here, which is quite important. Now we love a good graph, so here's a graph of your stress over your strain, and what you end up getting is a region just like in Hooke's law that's directly proportional, which is really nice. And then you're going to end up giving just a little bit of force, but it's going to go under a lot of strain. So essentially, you're going to apply a stress, which is an F over the cross-sectional area, and get a whole lot of strain, which is unitless, but the only thing that is measurable is your delta x, because L is fixed. So you can see the similarities. You can see how this falls out of Hooke's law. What does that mean for us mathematically? Well, let's remind ourselves what stress and strain are. You've got stress, and you've got strain, which is given as x delta L. And keep in mind here, before I go much further, that your area is going to stay the same, your cross-sectional area is going to stay the same in your wire, and your L is going to stay the same in the wire. And this is why you can see that Hooke's law and these things go together. This Young's modulus idea go together. So if I have a stress over strain, we're going to denote that by E, big E, and it's going to end up mathematically as being F over A all over X over L. Now, if you write that a bit nicer, we've got F over A times L over X, so we can see what's going on. And you end up getting F times L over this AX, which is cross-sectional area, times a length, which is just the volume of extension. It's end up going to be a volume. This is called the Young modulus. Keep in mind that it's Young, not Young's, so it's just the Young modulus. Right, so let's look at this Young modulus in a little bit more detail. We've got E is FL over volume. But that only tells us a little bit of the story because we have to keep track of what's constant and what's not. And as I alluded to before, if you keep your area constant and your length constant in a wire, then you can measure the other things and you should be fine. You should be able to calculate your Young modulus. So your area is going to stay the same, your length is going to stay the same, and the only things that are left to measure are your force and your extension. Now your force might be m times g, so that might not change too much. So really you're just looking at your extension, which is kind of awesome. So let's look at a typical curve of a typical material, and you'll end up with a region of Hooke's law, where your material follows Hooke's law, and your stress over strain is directly proportional. Then you're going to reach your elastic limit, and then your material will start to weaken until it gets to a yield point. Then you'll find that your strain will keep increasing to a point at which your gradient becomes massively shallow on your force side, but keeps extending until you get to a point of ultimate tensile stress. And this is the thing that defines the strength of the material. And then the last region you have to worry about is this little yellow bit where you undergo a bunch more strain and your stress varies a little bit until you get to a breaking point, or the breaking stress. Now go ahead and take a sec to copy this down in your books. Now let's look at some examples of the Young modulus of some real materials. Let's check out glass. Glass will undergo a Hooke's law proportionality for a little bit, and then it won't get to a yield point, it'll just break. It'll just pop because it's so brittle. Now that's very unlike copper, which will undergo a very low amount of force for a big amount of stretch, so your stress over strain curve gradient is going to be a lot shallower, and then it will bend for a while before it too breaks. And lastly, steel is very brittle, so its Hooke's law, or its constant, is going to be very steep, and then it'll undergo the same sort of behavior that was in the previous graph, and it too will finally break. So something that's brittle breaks before it hits a yield, so it doesn't really have a yield point at all. An example of this is glass. Materials could also be described as ductile, for which we get the full Young modulus curve with all the bumps in between. And the more ductile it is, the lower the gradient, or the lower the Young modulus E. And this is because you need less stress required for big extension or big strain. An example of this is a copper wire, and ductile is usually a word to describe wires. So the last little bit you need to know about Young modulus is loading. And what loading is where we put a wire under load, or a piece of rubber, or the other example in your book is polythene or plastic. So let's consider the same graph we've had all the way along, except for now your axes are going to be more like Hooke's law. So you've got your force and extension. And let's consider your wire for the first example. So for this, you recall that your Hooke's law area is followed under load until you get to your elastic limit, and then it'll undergo some sort of plastic deformation. And the interesting bit is when you get rid of the load, you let it go, if it hasn't reached its breaking point, the wire won't return to its original space because we've come off of the Hooke's law proportionality region. So your force will let go and your extension will come back near zero, but it'll go parallel to the curve you had before, not following it exactly. And now what you've got is a remaining extension. So that little bit of wire is now extended this distance here. It's got a permanent extension. So let's look at the case of rubber. So we've got our little rubber band back, and we've got our same F and delta X axes. And when we put this under a load, we're going to end up with a curve that looks like that. And I haven't got to its ultimate tensile stress or its breaking point. I've just taken off the load. So now, as I take off the load, a lot of the energy under this curve is going to be transmitted as heat. And so with a reduction in force, I start to lose some of the extension as well until it gets back to my beginning point. These two are supposed to be at the same place. We say that rubber has a low limit of proportionality, or a low elastic limit. And here I've given you a screenshot of what the limit of proportionality means. It's just a language exercise describing elastic limit. In fact, it's taken from BBC Bite Size, so it might be familiar to you from GCSE. The last material we have to think about is polythene. So polythene or plastic. And this undergoes the same sort of curve as rubber, but then it doesn't reform at all, and it just tanks right back into the delta X. So it extends and then stays extended, basically. And we say this because it retains the internal energy in its bonds. So it gets way up here in this region and it retains its energy and then doesn't go back.